Some theorists are now revisiting the idea of the Big Bounce, an alternative to the Big Bang.
5, 4, 3, 2, 1, 0.
Recent events have cast doubt on some aspects of this idea. In March 2014, the BICEP-2 group from Antarctica claimed to have detected cosmic gravitational waves, some touted as the conclusive proof of inflation. However, it was later revealed that the observed waves were not cosmic in origin, but patterns created by light passing through the dust of our galaxy. Instead of proving inflation, this discovery raised more questions. Recent findings have set stringent limits on gravitational waves, excluding many simple inflationary theories. This led to a renewed focus on the foundational assumptions of the Big Bang theory. Some theorists are now revisiting the idea of the Big Bounce, an alternative to the Big Bang. In this model, the universe's smoothing and flattening don't result from a high-energy random quantum origin. Instead, it emerges during a time resembling our present, where classical physics dominates. This model proposes that the universe undergoes periods of slow contraction instead of rapid expansion, eliminating the multiverse concept caused by random quantum fluctuations during inflation. The Big Bounce theory also has its predictions. It suggests a universe devoid of cosmic gravitational waves because of the absence of energy concentration. Multiple experiments are ongoing to determine the presence or absence of these waves. Another significant component of this theory is the idea of a cyclic universe, where the universe undergoes periodic bounces. This proposition is currently being tested through experiments and observations. The findings from these studies will not only determine the origins and future of the universe, but will also establish the relationship between gravity and quantum physics. These discoveries will shape our understanding of the universe's nature. If the multiverse theory is correct, our observable universe might just be a random occurrence, detaching us from understanding its fundamental creation. But if the bounce theory is right, our observations would represent the universe as a whole, giving insights into its fundamental laws.
What if the Big Bang wasn't the start of everything, but just a moment in an endless cosmic cycle? A new theory called bouncing cosmology suggests the universe may alternate between phases of contraction and expansion, challenging the idea of a singular beginning. This concept could potentially explain some of the biggest mysteries in astrophysics, like the nature of dark matter and the formation of black holes, suggesting they may have formed before the Big Bang in a prior cosmic phase. Recent studies and the development of future gravitational wave observatories, such as LISA, aim to test these groundbreaking ideas, potentially revolutionizing our understanding of the universe. In this video, we'll explore what bouncing cosmology is, how it might provide a solution to the dark matter puzzle, and what future discoveries could mean for science. The bouncing cosmology theory presents a revolutionary perspective on the universe's origins and evolution. Unlike the traditional Big Bang theory, which posits a singular beginning followed by rapid inflation, the bouncing model suggests that the universe undergoes a cyclical process of contraction and expansion. This model posits that instead of emerging from nothing, the universe transitions from a phase of contraction, where it reaches an incredibly dense state, to a bounce that triggers the expansion we observe today. This concept fundamentally challenges the long-standing idea that the universe began with a single, unrepeatable event. To grasp the significance of this theory, it is essential to consider the limitations of the Big Bang model. While the Big Bang theory provides a robust explanation for the observable expansion of the universe and the cosmic microwave background, it leaves unresolved questions about the cause of the initial singularity and why the universe appears so uniform on large scales. Bouncing cosmology offers an alternative perspective by suggesting that the universe's current state is merely one phase in an infinite cycle. This idea bypasses the problematic beginning of time and implies that the laws of physics we observe today may be deeply influenced by conditions from a previous cosmic era. A crucial aspect of the bouncing cosmology theory is the concept of a non-singular bounce. At extremely high densities, quantum gravitational effects come into play, preventing the universe from collapsing into a singularity. Instead, these quantum effects cause a bounce, leading to a new phase of expansion marked by the emergence of photons and particles. Within this framework, what we traditionally refer to as the Big Bang is not the universe's beginning, but a transformation from a previous contraction phase to our current expanding universe. This cyclical model suggests that each cycle of contraction and expansion could influence the next, pointing to a more interconnected universe across time. It implies that the seeds of galaxies, stars, and planets we observe today could have been laid down in a prior phase of the universe, shaping its evolution across successive cycles. Mathematical calculations and simulations support this model by predicting specific patterns in the distribution of cosmic structures, such as galaxies and the cosmic microwave background. One of the most exciting possibilities emerging from the bouncing cosmology model is for understanding the universe's early conditions and linking them with events preceding the Big Bang. This would suggest that the origins of the universe itself are more complex and interconnected than currently understood. Research in this area is already advancing, with scientists developing new models to better understand form and persist over billions of years. Researchers are also searching for indirect evidence of these through their interactions with stars, gas clouds, and other cosmic structures. To confirm or refute the bouncing cosmology theory and its implications for dark matter, scientists need to detect specific types of evidence. One of the most promising methods is through the observation of gravitational waves, ripples in spacetime caused by massive cosmic events like the collision or neutron stars. According to the bouncing cosmology model, the formation of primordials during a contraction phase would have generated a unique spectrum of gravitational waves, distinct from those predicted by standard cosmological models. If these waves exhibit the patterns predicted by bouncing cosmology, it would challenge the inflationary paradigm and offer a new understanding of the universe's structure and origins. Such discoveries would not only validate the bouncing model, but also redefine the fundamental principles of cosmology, potentially merging quantum mechanics and general relativity in ways that current models do not fully account for. Moreover, the search for these gravitational waves is already underway. Scientists are analyzing data from existing gravitational wave detectors for any signs of these primordial signals. While some interesting candidates have been identified, more data and more sensitive instruments are required to confirm these findings.
If you'd like to support the channel, links are in the description.